You can start.
Okay, welcome everyone to the third and last seminar on the results from the second LIGO-Virgo gravitational wave catalog. My name is Max Easy. I'm a NASA Einstein Fellow at MIT, and I will be your moderator for today. Before we get started, do note that this webinar is being streamed both on Zoom and on YouTube. Those of you on Zoom will be able to type in your questions into the Q&A box, and we will do our best to answer them during the presentations. We will also have a few minutes of dedicated Q&A time at the end of the event. What brings us here today is this latest paper on testing general relativity with the binary black holes from GWTC2. As you know, testing general relativity is one of the main objectives of gravitational wave science. And we can go about doing that by comparing our data against the very specific predictions that we get from the theory for the types of signal morphologies that we should see in our data. So this is an example of a waveform predicted by general relativity. We can look for deviations away from this prediction and see if the data favor that. In this paper, we do that in 8 different ways. And these 8 different tests, which are designed to target different parts of the signal morphology, are sensitive not also to deviations from general relativity, but more generally to any sort of modeling shortcomings that will show up as systematics in our detections. GWTC2 brings with it many, many new signals, but due to computational constraints, we choose to focus on the most significant binary black hole events. So we look at everything that has a false alarm rate of better than 1 per 1,000 years. And that leaves us with 24 binary black hole events that we look at in detail in this paper. We use that to produce event by event results from all of these 8 tests, but we also combine all of the different events together when possible to make statements about the joint distribution of measurements. You will be hearing about all the details from our panel from today. We have 4 panelists that will be fleshing this out. Serguei Ossokineand from the Albert Einstein Institute in Potsdam, Geraint Pratten from the University of Birmingham, Rico from the California Institute of Technology, and Anuradha Gupta from the University of Mississippi. Needless to say, we are all extremely happy to be representing the work of the many, many LIGO-Virgo colleagues that have made this possible. To get started, I will hand it off to Serguei, who will start telling us about the most generic type of tests that we carry out, the consistency tests. So Serguei, take it away.
Hi, everyone. Next slide, please. I am Serguei Ossokineand, and I'm going to take you through the consistency tests. The first test I'd like to talk about is the Residuals Test. The idea of this test is to subtract the best fitting, so maximum likelihood template, from the event's trained data, and then examine the residual coherent power. An example of this is shown in the plot on the right. For data around GW150914, here what is shown is the power in the time frequency plane. In the top, you can actually see the signal, whereas the bottom shows what happens when we subtract the best fitting GR template. To be more quantitative, what we actually do is that we compute the 90% upper limit on the residual SNR using Bayes wave. And then we want to compare this to the SNR we expect from noise. To do so, we examine about 200 times around each event, and again compute the SNR, which allows us to construct a p-value. So the probability that we can get an SNR equal to or greater than the residual SNR just from noise. Now, if the GR model is a good fit to the data, then we expect two things to happen. First of all, there shouldn't be any correlation between the SNR of the event and the residual SNR, since the residual SNR should be only a function of the state of the detectors at the time. And of course, we should find that the p-values indicate consistency of the residual power with noise. Next slide, please. The plot on the right shows the residual SNR, so the 90% upper limit, as a function of the SNR of our best fitting template. Here, the two diamonds correspond to the lowest and largest p-values, with blue being the lowest and red being the largest. And the open circles are events from GWTC1. From this plot, you can see that our first expectation is indeed fulfilled. There's indeed no correlation between the SNR of our GR template and the residual SNR. Next slide, please. Now, the table on the left shows all the events under consideration and the corresponding SNR, the residual SNR, as well as the p-values, again highlighting the lowest and highest p-values in blue and red. The most important thing to take away is that all the p-values in this table are consistent with all the coherent power, residual power coming from noise fluctuations in the detector. If we assume that this is indeed the case, then we expect that the p-values are distributed uniformly between 0 and 1. To test this, we create a PP plot, which is shown on the right, where the null hypothesis, being that all the coherent power, residual power is coming from noise, is the dashed diagonal line, and our measurement is the blue solid line, which one can see lies within the uncertainties, which are the band, consistent with the null hypothesis. So we can conclude that we find no deviations from GR with our residual test. Next slide, please. The second test I want to describe is the in-spiral merger ring-down consistency test. If general relativity is correct, then the final state of a binary black hole merger should be a Kerr black hole, which is uniquely specified by its mass and spin. These final mass and spin can be inferred from both the low frequency and high frequency regime of our signal. And the two estimates should be consistent with each other. So what we do is that we use parameter estimation on the full signal and some numerical relativity calibrated fits to infer the final masses and spins, and use those to construct a cutoff frequency, which I denote here by FC, which splits the waveform into an in-spiral and a post-in-spiral regime. And you can see that shown pictorially in the waveform plot. And once we have this FC, we repeat our procedure, first using frequencies below the cutoff frequency to obtain an in-spiral estimate for the final mass and spin, and then above the cutoff frequency to get the post-in-spiral estimates. Next slide, please. From these, we construct dimensionless deviation parameters, delta MF over MF and delta KF over KF, that we'll actually examine as deviations from GR. For the IMR test to be applicable, of course, both the in-spiral and post-in-spiral regimes must contain enough information. As a proxy for this, we impose a cut on SNR. In particular, we demand that both the in-spiral and post-in-spiral regime have an optimal SNR above 6. Additionally, we find that we need the events to have the detector frame total mass to be below 100 solar masses to avoid a large bias. This is because for events larger than 100 solar masses, the in-spiral is quite short. Finally, unlike results in the GWTC1 paper, we actually reweight the posteriors using priors which are uniform in the deviation parameters, which are defined on the left. Next slide, please. Before diving into the results, it's worth taking a step back and considering the issue of waveform systematics, which will come up a few times for different tests that'll be covered in this webinar. Now, the general relativity waveform models that we use for our analysis do not exactly correspond to the true GR signal. And this is due to two considerations. First of all, the approximations that we make when we construct these models. So for example, the theoretical underpinnings like post-Newtonian theory, exactly how we assemble our model, how we incorporate numerical relativity information, how accurate that information is, etc. And the second consideration is the physical content of the model itself, such as whether we include modes beyond the dominant quadruple, we allow precession of the orbital plane and the spins, and others. Of course, any such systematic effect will affect tests that seek to measure deviations from general relativity. So in order to gauge the impact of such uncertainties, we usually perform our analyses with multiple independent waveform models, and then look at the impact systematics have on the final results. And this is something you will see for other tests as well. Now, the three most frequently encountered families, some of which you will see in this webinar, are IMR Phenom, which is a phenomenological PN-based model, including calibrations to numerical relativity, the SEOB family, which is the effective one-body models that remap the relativistic two-body problem to an effective one-body problem, also including calibrations to an R, and finally the NR surrogate, which directly interpolates in our waveforms where those are available. For the IMR consistency test that we're talking about, we use two waveform models, IMR Phenom PV2 and SUBNR V4 ROM. Next slide, please. So without further ado, let's look at the results. Here, what's shown are the 90% credible regions in the delta MF, delta KF plane. So the GR prediction here would be 0, 0. And you can see these 90% contours. Here, the colors represent the detector frame total mass. You can see that almost all the events enclose the true GR value. The two events that do not are 1908-14, which has a low detector frame total mass and some prior effects in the post-inspiral analysis, known effects. And the second one is 1708-23, which actually does include the GR value at the 93% level. Now, of course, we want to combine all the results together. If we make a restrictive assumption that the deviations are actually shared among all the events, then we can go ahead and just multiply all the posteriors together. And that's what's shown as the gray band and the gray distributions. And you can see that indeed everything is consistent with general relativity. Now, the results that are shown here are with the IMR Phenom PV2 waveform. If we repeat the same procedure, we get the results in the next slide. Here, we see the results with SUBNR V4 ROM, and the most important thing is that they're qualitatively consistent with what we saw in the slide before. Next slide, please. Now, we want to remove this restrictive assumption that, in fact, we have shared values of the deviation parameters. In order to do so, what we do is that we model the deviations for every event in our pool as coming from a joint distribution, common distribution, which we take to be a Gaussian distribution with an unknown mean mu and standard deviation sigma. General relativity would be recovered for this particular test when both mu and sigma are 0. When we have the distribution of mu and sigma, we can go ahead and actually marginalize over these population parameters. So this is what's given by this integral. Here, x represents either delta mf over mf or delta kf over kf, and we do the analysis separately for the two deviation parameters. The results are shown in the figure on the right. Here, the solid lines are the results from GWTC2, while the dot dash lines are for GWTC1. We find that the results are completely consistent. So the fractional deviations are consistent with 0, that is with general relativity, and that compared to GWTC1, the posterior for the for the final mass is slightly narrower. So we have improved the accuracy of this test. Just to conclude, I would say that we find that general relativity is completely consistent with the results of our IMR consistency test. And now I'm going to pass it on to Geraint, who is going to describe source dynamics.
Hi, so I'm Geraint Pratten, and I'm going to be talking about parameterized tests with gravitational wave source dynamics. If you can go to the next slide, please. But first of all, why do we consider parameterized tests? Well, unfortunately, we still lack a suite of mature alternative theories of gravity, and there's a number of theoretical obstacles, such as are these theories well posed? Are they physically viable? And importantly, do they provide well-defined predictions for the emitted gravitational wave signal from a standard compact binary coalescence? So there's still a significant amount of work required before we see the widespread use of beyond GR models in gravitational wave data analysis. So with these restrictions in place, what can we do? Well, first of all, we're restricted to testing the null hypothesis, which we take to be general relativity. And this means that we can then aim to quantify generic deviations from the GR predictions. So we're essentially constraining the degree to which these deviations agree with the data. Now, for parameterized tests, we can gain a lot of insight into the anatomy. We can gain a lot of insight into the structure of the parameterized test by studying the anatomy of a compact binary coalescence. So here I've plotted a numerical relativity waveform, and there's a number of key different regimes that come into play. And these will set the structure for these parameterized tests, as I said. So if we start off from the first on the left-hand side in blue, we have what's called the in spiral. So this is when the two objects are sufficiently far apart, they're orbiting each other and emitting gravitational radiation. Now here we say that they're moving slowly, so the velocities are below the speed of light. And this means that analytical approximations, such as post-Newtonian theory, are applicable. This is a perturbative expansion of the Einstein field equations, empowers the velocity over the speed of light. Now, as the binary in spirals, the velocities can become comparable to the speed of light, and this means that this perturbative expansion breaks down. So now we're hitting this green regime where approximations are beginning to fail. And this means that we must appeal to numeric relativity simulations to really understand the physics and the structure of this merger regime in red. So this is when the two black holes plunge and merge to form a single perturbed black hole that will shed itself of deformities by emitting gravitational radiation, and this is the ring down, and we'll hear more about that later on. But these different regimes all set the structure for the parameterized tests. So if we go to the next slide, we see that we can write an in-spiral merger ring down waveform in terms of frequency-dependent amplitude and phase. Now we could consider corrections to both the amplitude and phase. Here we consider only phase corrections. Amplitude corrections are something that we're in principle less sensitive to and can also in part be reabsorbed into what the uncertainty on the detector response. Now, if we look at the phase, we can use the insight from the previous slide to break it down into three distinct regions. Now, the first region, as I said, was this in spiral. This is this slow motion regime where the coefficients are analytically known in general relativity through the post-Newtonian approximation. So this is a perturbative expansion in terms of powers of the velocity, or equivalently in terms of the gravitational wave frequency. So here we have various post-Newtonian coefficients, and these various coefficients encode different physical effects. So we have different types of spin couplings, spin-orbit couplings, and so forth that occur at different PN orders. So higher PN orders, so higher corrections in terms of velocity over, etc., velocity of the speed of light, come in at higher powers of frequency. But this provides the perfect baseline into which we can introduce parameterized deformations. Now moving on, the next two regions, the intermediate and merger ring down, these are a bit more problematic. These are phenomenological in nature. So whilst they are designed to match the phasing from general relativity, there's this cautionary note on the right-hand side that we should really pay attention to, namely that the coefficients, whilst calibrated against numerical relativity simulations, so whilst accurate, are not expressed in terms of parameters that are relevant to either general relativity or any modified theory of gravity. So some caution has to be taken into account when we try to assign some sort of physical interpretation or meaning to these coefficients. So for the intermediate regime, this is just a simple phenomenological ansatz calibrated against numerical relativity, whereas for the merger ring down, we can again appeal to black hole perturbation theory to help set the structure of this equation, as well as some phenomenological coefficients. So if you go to the next slide, we can see that we can introduce we can perform a parameterized test by introducing a parametric deformation to this underlying GR model. And we do so by varying one coefficient at a time. This is not a unique choice. There are other choices we can make. We could perhaps vary multiple coefficients. In our analysis, we just vary one coefficient at a time. So these P parameters are our various coefficients, and they're exactly the coefficients I just introduced. The phi's in the in spiral, the beta's in the intermediate regime, and the alpha's in the merger ring down. If you're familiar with the literature, this is just a variant of the parameterized post-Einsteinian framework, so it probably sounds quite familiar to some of you. Now, we actually implement two independent approaches that use two different waveform models. In the first approach, we actually directly modify the post-Newtonian and conformational coefficients in the IMR phenol model that Serguei just introduced. And in the second approach, we actually add deformations that correspond to these post-Newtonian inspiral coefficients to some underlying SEOB waveform model that, again, Serguei nicely discussed. So this gives us 10 inspiral coefficients that we analyze with both the phenom and SEOB waveform models. This helps gauge against systematics and is a good cross-check. Certainly when we're looking for instance, a violation of general relativity, we do require violations to be seen in both waveform models, otherwise we perhaps have a problem. So the frequency scaling of these PN coefficients is given on the right-hand side. Whereas for the post-inspiral regime, this only occurs in the phenom model. These are phenomenological parameters that are exclusive to IMR phenom. So we have two coefficients, beta in the intermediate and three coefficients in the merger ring down. If you go to the next slide, please. So what we plot here is the 90% upper bound on these GR, sorry, 90% upper bound on the absolute magnitude of these GR violating parameters. So what we have here in the horizontal lines is each of the GWTC2 binaries that passes the threshold for inclusion in the parameterized test. And here they're colored by their redshifted chirp mass. So lighter binaries are in blue, heavier binaries in red. And what we typically find is that lighter binaries have better constraining power in the in-spiral and heavier binaries for the post-in-spiral. This is simply a consequence of how the waveform scales with mass. So as we increase the mass of a binary, it gets shifted to lower frequencies. So more of the post-in-spiral regime enters into the LIGO-Virgo sensitivity band. So this just means that you're sensitive based on the mass and the mass scaling. Now, the improvements that we see are consistent with the increase in sample size. This is your typical root N improvement. And we do find a broad improvement over GWTC1. So here the red dots correspond to the GWTC1 bounds, and the chevron on the triangle correspond to the updated GWTC2 bounds. Now for some coefficients, such as the -1 PN and the 0.5 PN coefficient, we find that the binary neutron star merger GW17 still dominates. This had a particularly long and loud in-spiral that really allowed us to pin down these post-Newtonian coefficients to really quite exquisite accuracy. Otherwise, we do see a broad improvement across the board relative to GWTC1. If we go to the next slide, please. As Serguei also discussed, we can start to stack the events and construct these joint posteriors, and we do so using the two approaches. The first is to assume the shared common value of the deviation parameter, and the second approach is this hierarchical analysis, this population-inspired analysis. This is something of a stricter criterion in the sense that both the distributions and the hyperparameters are required to be consistent with general relativity. So this means that these deformation parameters, these delta p's, must vanish, and the mean and the variance of the distribution must also be equal to 0. So plotted here, the dashed horizontal gray line corresponds to the GR limit of vanishing deformations, and the shaded regions correspond to these population marginalized expectations from a hierarchical analysis. So blue is for phenom and red is for SEOB. And the black distributions are when you assume the shared common value. So the left-hand side is for phenom and the right-hand side is for SEOB. And again, we find that everything is consistent with general relativity. We see this again in the next slide, where we again look at the hyperparameters, where the GR coefficient, as I said, was mu equals sigma equals 0. And we find that all the contours do contain the GR value. We see this for both phenom, for all coefficients, and we see the exact same result for SEOB, again, for all coefficients. So general relativity is extremely consistent. If you go to the next slide, please. Next up is the spin-induced quadruple moment. This is actually a specialized variant of the parameterized test that I just discussed. Now, the scenario here is that the spin in motion of a compact object will create a distortion in the mass distribution. And this distortion in the mass distribution then propagates through to the gravitational field and can be measured by something known as the quadruple moment tensor. Now, the key point here is that this whole effect gets imprinted in the emitted gravitational wave signal at specific PN orders. That's why it's a specialized variant of this parameterized test. Now, in our analysis, we include a leading order correction that occurs at 2 PN, as well as a correction that occurs at 3 PN. Schematically, for a compact object of mass m and dimension of spin chi, the quadruple moment tensor looks something like this, where the value of 1 is explicitly for a black hole, and then we have a delta kappa term whose coefficient depends on the equation of state, mass, or spin of the compact object. So this enables us to perform essentially a null test of the black hole nature of the compact object. So for black holes, as I just said, no hair conjecture means that this delta kappa is 0, But for neutron stars, boson stars, gravastars, or any other exotic compact object, this delta kappa can be non-zero. If you go to the next slide. So what we find is that this delta kappa term is unfortunately highly correlated with the masses and spins. And this means that we seek an alternative parameterization. This is analogous to how we define an effective aligned spin rather than individual spin components. So we introduce a symmetric and an antisymmetric kappa. Now, because for black holes kappa is equal to 1, the antisymmetric term implicitly vanishes, and we only consider perturbations to the symmetric term. Now, for black holes, delta kappa S is 0, so we have this nice GR limit. And in the left-hand plot, we show the analysis on the individual events, and you see that things are broadly consistent with general relativity. Sometimes the bands are a bit weak, and we've highlighted the most prominent events. And on the right-hand side, we have the same sort of picture that we considered before, which is that we can stack the posteriors, construct these joint posteriors in the two different approaches. So this restricted approach is for when you have the shared common parameter, and this generic is again hierarchical analysis. Key takeaway message is that the black hole hypothesis survives and that general relativity is doing an extremely good job. So this sort of summarizes the core conclusions from the parameterized test, and we'll now move on to the remnant properties with Rico.
Can people hear me now?
Sounds good now.
Oh, excellent. Oh, yeah. So let me take over and talk about remnant properties by analyzing the post-merger part of the signal. Next slide, please. So as Serguei and Geraint just mentioned, we expect signal from a binary black hole mergers to consist of 3 parts in spiral merger and ring down. And in particular for ring down, it is a linear superposition of quasi-normal modes of set frequencies and damping times. And by the virtue of no-hair theorem, these frequencies and damping times depend only on the final mass and final spin. And by measuring these frequencies and damping times, we can learn a few things. First, by assuming the remnant is indeed a curved black hole, we can actually infer the final mass and final spin independent of the spiral part of the signal, and that gives us some sort of an IML consistency test. And the second thing is that we can do a test of GR, where we compare the measured frequencies and damping time with GR predictions. Before diving into the details, let me qualitatively summarize the key results. The first thing is that the measurements of the final mass and spin, they're consistent with the measurement using the full IML signals. And the second is that the inverted quasi-normal frequencies and damping times are consistent with the black hole perturbation theory calculations. Next slide, please. So first, let's talk about measuring the remnant mass and spin. And here we are using 3 different ring down only waveforms. The first one is called the curve 2 to 0, which include only what we call the 2 to 0 mode, the least damped mode. The second waveform is called the curve 2 to 1, which include both the 2 to 0 mode and 2 to 1 mode. That is the fundamental mode and the first overtone. And the third waveform that we use here is called curve HM, which include all the fundamental modes up to L equals to 4. And apart from measuring the final mass and spin, we can also quantify the contribution of, for example, higher modes in ring down by comparing the evidence of the curve HM model with the curve 2 to 0 model. And similarly, we can quantify the contribution of overtones by comparing the evidence of the curve 2 to 1 model with the curve 2 to 0 model. Next slide, please. Here I show a visualization of the final mass and final spin measurement using the 3 ring-down-only waveform models, and also the measurements using the full IMR waveform. And here I'm showing the 90% credible interval, and the markers labeled the median. And on the left is the final mass in detector frame, and on the right is the final spin. Let's first look at the final spin. As you can see, we did not really measure the spin very well using the ring-down-only waveforms, but they are nonetheless consistent with the full IMR measurements. And on the left, we show the measurement on the final mass, and they are better measured compared to the final spin when using the ring-down-only waveforms, but they're also consistent with the full IMR measurements. Next slide, please. If we look at the column for the log-based factor of higher modes HM versus 2 to 0, where a positive value indicates that the data prefer the Kerr HM model more than the Kerr 2 to 0 model, and vice versa. And we can see that the values are all very close to 0, meaning that we do not see significant evidence of higher modes in ring down. And in particular, the highest log-based factor is just 0.61, which is small. Next slide, please. Now we can move on and talk about constraining the fractional deviation of the quasi-normal mode frequencies and damping time from the GR value. And here, we write the effective frequency and damping time as the GR values time 1 plus the fractional deviation. And for this particular analysis for the 2 to 0 mode, we are using the full IMR waveform, and we get the final mass and spin information of the black hole from the in-spiral part. And here, the plot shows the contour for the 90% credible region, and the gray line are showing the GR values, namely delta F and delta tau equal to 0. And using the hierarchical analysis, we constrain delta F 2 to 0 to be roughly 0.03 plus or minus roughly 0.4. And for the damping time, we constrain delta tau 2 to 0 to be 1.6 with a wider uncertainty of roughly plus or minus 1 using the hierarchical analysis that we just mentioned. Next slide, please. Here we did the same thing, but for the 2 to 1 mode, the first overtone. And in particular for this analysis, we are using only the ring down part of the data, where the final mass and spin are instead invert from the fundamental mode. And here we're only showing the contours for 3 events as examples, but we actually use more events in the hierarchical analysis for constraining the delta F 2 to 1, where we get the delta F 2 to 1 to be roughly 0.04 plus or minus roughly 0.3. But for delta tau 2 to 1, they're virtually unconstrained because they're very difficult to measure. And we can also compute a log-odds ratio to summarize the level of disagreement with general relativity of the 2 to 1 mode, and we get a value of minus 0.7, which show that what we observe are consistent with general relativity. Next slide, please. And next, let's talk about gravitational wave echoes. If the remnant compact object is not a classical black hole, and instead it is what we call an exotic compact object, where the would-be event horizon is replaced instead by a reflective surface. And we expect to see what we call echoes, which are essentially modulated and repeating quasi-normal modes after the ring down in the post-merger part of the signal. So instead of seeing in-spiral merger and ring down, we expect to see in-spiral merger ring down echoes, what we call the IMRE model. This is because the light ring of the exotic compact object and the reflective surface effectively form a cavity trapping the gravitational wave, and the echoes are the gravitational wave leak through the potential barrier. It would be a smoking gun evidence for a black hole mimicker if we detect these gravitational wave echoes. Next slide, please. So here we analyze 31 BBH from GWTC2, which include both O1, O2, and O3A passing the far threshold. And here, a positive log-based factor means that the IMRE model is preferred over the IML model by the observed data and vice versa. And looking at the table, we see that there is no significant evidence of gravitational wave echoes in the data. And in particular, highlight here the quote-unquote the most significant event, GW 190915, has a log-based factor of only 0.17. There are also two events that we did not include in this table, namely GW 151012 and GW 170729, because they did not pass the selection threshold, but nonetheless, they're of interest to the community because there are previous echo search applied to them. For both of the event, we are all seeing a negative log-based factor. And that concludes the remnant property section, and I will give the floor to Anuradha to talk about dispersion and polarization.
Thank you, Rico. So I'm going to talk about the dispersion of gravitational wave in the space-time between the source and the detector, and also the content of polarization modes in the gravitational wave signal. Next slide, please. So we know that when a white light passes through a prism, different frequencies refract at different angles, and it causes a rainbow. And this is because of a phenomena known as dispersion. Gravitational wave travel from sources to the detector, traveling long distances, and they can also disperse. And here we are testing whether the space-time has a frequency-dependent refractive index for the gravitational wave or not. So to do that, we employ a generalized dispersion relation as shown on the top left corner of this slide. And here A alpha and alpha are our phenomenological parameters in different theories of gravity, which include Lorentz invariance violating theories. Different values of alpha and A alpha means A alpha and alpha can take different values. For example, in GR, A alpha is 0 for all alpha values. And for example, in a massive gravity theory, alpha is 0 and A alpha has to be positive. And this also gives us the mass of the graviton. And note that the mass of the graviton is 0 in GR. Next slide, please. So in our analysis, we assume different values of alpha ranging from 0 to 4 in the step of 0.5. We do not consider alpha is equal to 2 case because in that case, the speed of gravity changes in a frequency independent manner, and it is totally degenerate with an overall time delay of the signal at the detector. We also assume that A alpha can be either positive or either negative. We also assume that the signal close to the source is given by GR, and any modification to the gravitational wave comes due to the propagation from the source to the detector. Dispersion of gravitational wave leads to dephasing of the entire gravitational signal, and this dephasing is proportional to A alpha, which also roughly scale with the distance to the source. So more the distance, more will be the dispersion, and it will be easier for us to find it in the data. A alpha and mass of the graviton are our analysis parameter, and we used flat prior for both the parameters. Since in any given theory of gravity, A alpha and mass of the graviton shared between all the events, so to get the combined result, we just multiplied the posterior from individual events and present in the paper. Next slide, please. So on the left-hand side, we are showing the Violin plot for the posterior distribution function for A alpha having both negative and positive values. Blue Violin is for GWTC2 and gray Violin is for GWTC1. And as we see that the blue violins are smaller, the size of the blue violins are smaller than the gray one, which suggests that we certainly have improvement in the constraint of A alpha value moving from GWTC1 to GWTC2. On the right, we are showing the 90% upper bound in the absolute value of A alpha, which is actually derived from the left plot. And the left panel is for negative values of A alpha, and the right panel is for positive value of A alpha. And the color again shows that the blue one is for GWTC2 and the gray one is for GWTC1. And we clearly see an improvement in the GWTC2 catalog. On the right bottom, we see the blue dot, which is for positive A alpha, and alpha is equal to 0. And this data point actually gives us the graviton mass. Next slide, please. So, so take-home message from this test is that there is a noticeable improvement in the upper bound of A alpha as compared to GWTC1. And this is a factor of 2.6 improvement. And this improvement is actually consistent with the increase of number of events from GWTC1 to GWTC2. We also computed the mass of the graviton, and we find it to be less than 1.76 times 10 to the power minus 23 electron volt per c square with 90% credibility. And this is again a factor of 2.7 improvement as compared to the previous catalog. If we compare this bound from other probes, such as the solar system bounds, we find that our bounds are 1.8 times more stringent than them with 90% credibility. So this was all about the dispersion. Let's talk about the polarization content and in the next slide. So generic metric theories of gravity can allow up to 6 gravitational wave polarization. This include 2 tensor modes with helicity plus minus 1, and these are also the only modes allowed in GR. Also, it contains 2 vector modes with helicity plus minus 1 and 2 scalar mode with helicity 0. And on the right, we are showing that these different modes, when present in gravitational wave, how they affect the ring of free particles when they pass through, when the gravitational wave pass through the ring. These polarization content of gravitational wave are imprinted in the relative amplitude of the detector data. And by using these relative amplitude, one can reconstruct the gravitational polarization content in the data. And to detect these modes, a 5 detector network would be ideal. But since we do not have a 5 detector network currently working, we have to make do with 3 detector network. And we try to distinguish between different specific subset of all the possible polarization combinations. Next slide, please. So in our analysis, we assume we have 2 extreme polarization hypotheses. The first one is the full tensor versus full vector, which means that the gravitational wave either contain the only 2 tensor modes or only 2 vector modes. And the second hypothesis is full tensor versus full scalar, which means that the gravitational wave either contain the 2 tensor mode or only contain the 2 scalar modes. So the polarization test is based on a null stream, which does not rely on any specific waveform model. A null stream is the linear combination of data stream from different detectors, and it is free from a true gravitational wave signal for a given helicity and sky location. But since we don't know the sky location of the source a priori, we marginalize the result over the sky location. And this is also the reason we could not we could test only the 2 hypotheses listed above. If we had known the sky location of the signal, we could have tested more hypotheses with different combination. So since the null stream shouldn't have a gravitational signal for a given helicity and sky location, any excess power in the null stream must be produced by a different helicity and sky location. And we quantify this excess power in terms of null energy, and we try to constrain this quantity using the data. Next slide, please. So we are computing base factor for the 2 hypotheses. The first one is BTV for the full tensor versus full vector hypothesis, and the other one is BTS for the full tensor versus full scalar hypothesis. And on the left, we are showing the log base 10 base factor for all the events. I've also listed the highest base factor and the lowest base factor events. But in general, the base factors are very small for all the events, and it suggests that none of the non-GR hypotheses are preferred with high significance. On the right, we are showing the distribution of base factor for the two hypotheses. The blue one is for the full tensor versus full scalar, and the red marker is for the full tensor versus full vector. And we see that the scalar, the blue points are very much different than the red points, but if you notice the range of base vector, it is very small. And again, the results are not very conclusive. But the difference between the blue point and the red points can be explained by the intrinsic geometry of antenna pattern for the LIGO-Virgo detector, which suggests that it is easier to distinguish the scalar modes in the data. Our bounds here are somewhat less informative as compared to the previously reported bounds, and this is because in our method we do not rely on a specific waveform model, and the only thing we use is the data, and data has noise, and hence the bounds are weaker. And we hope that with in future with better quality data, then the bounds will improve. So I will, this was all about the polarization. So I will now hand over to Max.
Okay, I will briefly conclude by noting that out of the 24 events that we have looked at, and this using these different 8 different tests that you just heard about, we have found no statistically significant evidence for deviations from general relativity or for unknown systematics. However, we have used our results to improve the constraints on some parameters of interest with respect to our previously published results with GWTC1. And that includes, for example, the post-Newtonian coefficients governing the dynamics of the source, or the parameters controlling the dispersion of gravitational waves. And we are tightening these deviations on these parameters with respect to the prediction from general relativity by factors of 2 or 3, depending exactly on what number you're looking at. But this is not just more of the old stuff. We have a lot of new content in this paper discussing new analyses that were made possible by the increased number of gravitational wave detections, but also by the greater range in their properties. For example, having more massive systems allows us to take a deeper look at the remnant properties, which you heard about when we talked about ring downs and echoes. And we also have the test of spin-induced quadruple moment, which we had not carried out in the past. We have also introduced a number of new statistical techniques in the area of testing general relativity to actually leverage this large population of signals. And this will become more and more important as we continue to detect more events. So note that this was about all about the first half of the third LIGO-Virgo observing run. Our colleagues and us are already hard at work processing the second half of the third observing run. So you should stay tuned because there's a lot more to come. With that, I will open it for questions. If you have any, please type them into the Q&A box and one of us will answer them. Let me see. Okay, we have a question from Zen Pan for the dispersion test, A alpha PC to the power of alpha. How can the two parameters A alpha and alpha be constrained at the same time? If alpha equals 0, alpha should be completely unconstrained. We do not constrain A alpha and alpha at the same time. For each power of alpha, we constrain what the prefactor A alpha is. So alpha itself is not a parameter that is sampled over. The next question from Hirotaka Zusurihara. In these talks, the base factors often used to compare the models. Is there a quantitative threshold on base factors to throw away except one of the models? Perhaps Rico would like to answer that.
I hope that people can hear me.
Yep.
So at least for the echoes, we actually have what we call the background of the base vector, where we sample we just run the same analysis, but over a segment of noisy data containing only noise, and see what the base vector would look like, and then we can quantitatively to set a threshold for base factor. In the context of echo, that would be the base factor for IMRE versus IMR. For other, so as you mentioned, there are other analyses also using this base factor to do hypothesis or model selection. For that, we do not actually have like a background distribution for the base factor, and we often use some rule of thumb. For example, I think it is commonplace to say that we would consider log base factor of roughly 2 to 3 to be significant. So yeah, hope that answers your question.
Okay, I believe I will give 30 more seconds if anyone wants to type any further questions. If not, this concludes our seminar for today, as well as the series of webinars on the LIGO-Virgo results from this GWTC2. We thank you for joining us and have a good day. Goodbye.